Good morning, everybody. It's 9 a.m. here in San Diego, so we will begin the webinar. Thank you very much for joining us. Today's webinar is on ligand-based lead discovery using atomic property fields. Atomic property fields is available in our products ICM Pro plus Chemistry or ICM Chemist Pro. My name is Andrew Ori, so if you have any questions after the webinar, please feel free to email or give me a call. During the webinar, you can use the chat or the questions panel to ask questions. I'll try to address them as we go, or at the end, or via email after the webinar. If you want to follow news from MolSoft's, please follow us on these social media sites. And a 30-day ICM Pro license is available for webinar participants. If you haven't already received it, there's a little bit of a backlog, but I will get to it soon. So we're going to start. Just to let you know that the recordings of the previous webinars are all on our YouTube site. So we started actually 6 weeks ago on ligand docking using ICM. We covered virtual ligand screening of large compound databases and how to analyze the results and build hit lists and select compounds for testing. Then we covered how to incorporate induced fit or flexibility within your docking, how to use multiple receptor conformations, how to allow certain residues to be flexible during docking. Then we covered covalent docking and fragment docking and linking. And then last week, not shown on here, is the 3D ligand editor where you can optimize and design your own ligands. So they're all on the YouTube site. So today we're going to cover atomic property fields, APF. We're going to look how to use APF for chemical superposition, how to generate a consensus APF 3D APF pharmacophore, how to perform multiple chemical alignments, and also virtual screening using atomic property fields. So you can take millions of compounds and screen it against an APF 3D pharmacophore field. How to perform chemical clustering using APF. So sometimes if you have a structure-based screen and you have a hit list, you could do substructure clustering, for example, to generate a more focused or diverse library. So yeah, you're going to select a diverse library from different clusters. But you can also cluster by atomic property fields, so we'll show you that as well. And then if you have enough data to build a QSAR model, you can use APF to generate 3D QSAR models and predict activity. So what is atomic property fields? APF is a 3D pharmacophore which replaces discrete points by continuous property distributions. So by this we mean sort of a multi-component 3D potential that reflects preferences for various atomic properties at each point in space. So APF replaces representation of chemical moieties with fixed pharmacophore types by vectors of atomic properties that can be compared in a more flexible quantitative manner rather than just by matching the chemical moieties. So it enables you to dock these ligands in these fields and also for superposition. I should point out that the paper, I'll provide the paper in the email following up on this webinar. That was by the method is developed by Max Totroff, and it's described back in 2008 in this journal here. So if you build an APF potential, there are 7 different components to that field. There's hydrogen bond donors, hydrogen bond acceptors, sp2 hybridized regions. You can map the 3D lipophilic regions. There's an element of size as well that's incorporated into the component. And then there's obviously electropositive and electronegative regions, as well as charge itself. So here we have ciprofloxacin, which is a useful chemical because it actually contains all 7 pharmacophoric components. So we could just quickly look at that in ICM now. So it's going to close this. Yeah. And so we're going to sketch superposition. So we go to the chemical editor here, this button. You get the slight ChemDraw sort of window. It's actually all developed by ICM, but it has a inbuilt in it is a chemical dictionary which you can search, or you can obviously sketch the molecule yourself if you wanted to. So it's sketched. It actually has a positive charge here, so we need to right-click and choose positive charge, and then we can commit this to a chemical spreadsheet by just clicking on this button here. It's append, give it a name. It's an antibiotic. I was going to give it any name you want. So you have the table. We have it in a chemical spreadsheet. But in order to generate the chemical fields, we actually need to convert it to 3D. So besides that button here, we have this button here which says Convert Molecule to 3D. The one next to it will generate multiple 3D conformers. This is just going to report the best energy one. So we're just going to click on here and go OK. And it's converted the molecule to 3D. So just to look at the property fields of this molecule, we need to select it in the ICM workspace on the left-hand side. So selection is just double-click. That selects. You see blue selection here, green crosses here. And then we go to Chemistry, go to APF Tools, and choose Consensus Pharmacophore. Now, if we had in an ideal situation, if you're doing virtual screening, you might have more than one template. So you might have more than one molecule superimposed. And so you can color it by a certain threshold where you can say, I want to see the donors within that are conserved within 75% of my alignment of molecules. But we only have one in this case. So we can just go OK. And this generates the 3D the APF fields. And you can then see on the left-hand side, which we have a new element to our ICM workspace called meshes. And so we can see the hydrogen bond donors are in blue mesh, the acceptors are in red, the negative charge shown here, the positive charge you can toggle on and off and display, the aromatic and the lipophilic and the size parameters. So that's basically your field. So you could, in theory, you can go to Chemistry. We'll do this in a bit, and you can screen. You could screen to this molecule, or you can superimpose into these fields, which we're going to do in a bit. So just going to go back to the slides. So once you've generated the fields, what can you do with them? So there's lots of the APF pharmacophoric potential is implemented on a continuously distributed grid and can be used for ligand superposition. So you could take a ligand from the crystal structure in an energetically favorable pose and then superimpose other chemicals on top. If you didn't have the crystal structure ligand, you can just do a multiple compound alignment based on APF. And if you have this alignment generated from this superposition or from this multiple compound alignment, you can then do virtual screening into those into that alignment, into those superimposed chemicals, and then get a score and find chemicals that have similar pharmacophoric properties in your screening set. You can also use it for 3D QSAR. We'll cover that as well. Another application which we won't cover today but is very useful is you can use atomic property fields for superposition of protein binding sites, whereby the proteins sequentially and structurally are not similar, but they are similar in the terms that they bind chemicals with similar 3D pharmacophoric properties. So you can use the pharmacophoric properties of the pocket and superimpose based on those pharmacophoric properties, and superimpose structures, protein structures, which are otherwise quite hard to superimpose because there's no sequence similarity or structure similarity. So, and that's described by Max Totroff in this paper back in 2011. And the option there is in Tools, Superimpose Sites from APF, if you want to try it. Okay. So we recently had great success in the D3R docking challenge, which is an industry-wide docking competition, and ICM ranked first place in prediction of RMSD of ligands, the average RMSD of ligands shown here. Our solution was here. These are the other 50 groups that went into the competition. We also did very well in the binding energy prediction as well. And one of the reasons for that success was that the method that Max Totroff and Polo Lam and Ruben Abagayan used was a combination of atomic property fields, APF, as well as structure-based screening. So and this method is described in a very recent paper here, which I'll provide after the webinar as well. And there's also APF was also compared to some other programs such as Surflex, ROX, FlexX, and DOC. And this was an independent evaluation by a group in France, and you can read this paper here. But anyway, APF, which they called in those days, this was 2010, ICM Sim, provided for chemical superposition of active compounds. APF was found to be the most efficient for chemical superposition, and also had a very good enrichment factor, or an enrichment at both 1% and 10% enrichment for virtual screening. So our next example is how to do chemical superposition, and we will use a non-trivial superposition example of two non-nucleoside reverse transcriptase inhibitors shown here, which actually would be quite a challenge to superimpose these molecules if you were just trying to superimpose based on substructure. But in actual fact, when you look at the crystal structure, they do superimpose very well based on their pharmacophoric properties, and we're going to go through that example now. So let's just go to the example. Okay, so here in 3D we have one of the, I'm just going to close the PowerPoint. We have one of our lead molecules. This is from a crystal structure. It's actually from PDB1RT4. So basically I just read in the PDB and extracted the ligand and converted the ligand to an ICM chemical. I'll show you how to do that in a minute. So this is what we call our template. So we're going to try and superimpose this other inhibitor, a HIV reverse transcriptase inhibitor, onto the structure, onto this template. So you can see that the different it would be hard to maybe some talented chemists could probably work it out, but generally by substructure it would be hard to try and superimpose or align these chemicals. So what we're going to do is we're going to align them. So we need to go to the chemistry menu and go to superposition, and there's inbuilt into this superposition dialog there's other non-APF tools. You can superimpose by common substructure, but we're not going to do that. You can do flexible superposition. You can superimpose two molecules by APF alignment, but what I'm going to use is flexible APF superposition to the template. So we're going to flexibly dock this ligand into the 3D pharmacophoric properties of this ligand we have here. So we first need to make a selection. So we need to double click on our template, and then go to chemistry, superposition, flexible APF superposition to template. And then we get some questions. It asks us which chemical table we want to dock or to superimpose, and it's called this matches. The template is one molecule. The effort is the length of the simulation. APF is very quick, so it's less than a second per compound usually. So you can increase this effort without increasing the time too much. So it's ideal for screening millions of compounds because you can get through millions in a very fast time. So you can also choose whether you want rings to be sampled or cis-trans. And then you can say whether you want the superposition to be scored. So in this case we're going to do that, so you just click here. So about the score, the lower the score that you receive, the better the fit with the template. But no one score or threshold can be stated as being a good score. So it really depends on the chemical types that are being superimposed and the template. So one way to tell whether an APF score is good or bad is to compare it to the score obtained when you self-superimpose. So if we had this ligand in the table here, if we superimpose it and generate the score, that would give us a threshold for the score and what kind of area we need to be in. Generally it's going to be around 150, something like that, minus 150, something like that, or more, or less, sorry, or less. So you can also sample tautomers, you can score. Another score is not only how well it fits into the pharmacophoric properties, but how well it actually fits into the envelope of the 3D environment. How, is the ligand pointing out of the fields or not? That will give you another score. There's some advanced options where you can weight by lipophilic weight or polar weight. And you can also, like with docking, you can load in a template and use that as well to guide the superposition if you need to do that. We're not going to use those cases. So we just go OK, and it will start the superposition. Now it's finished, and you get a table shown here with the docked ligand and the score. So this one has a score of minus 170. We can toggle the display of the superposition by clicking here. And I'll show it here. So we're going to compare this now, the superimposed with the crystal structures. I'm just going to rename this ligand. Right click on it and just superimpose. So now we can read in the crystal structures. So this is 1RT4. So we just go to the PDB search, type 1RT4. Press enter, and it's here. And the other one is 1TL3. The one we docked is from 1TL3. So we need to superimpose these two structures. So we can do that by selecting the A subunit of one and the A subunit of the other by using the control key. You can select non-contiguous selections just by double-clicking here and here, and then go to display and superimpose, and that will superimpose those two chains. And now we can look at compare the one we just docked, which is called TL3 superimposed, with the ligand where it's actually bound. It's from this one, so that's going to display this. Uncheck this, and if we just double click on the ligand and then press the center button, that will take us in, and you can see that the compound is pretty well superimposed with the crystal structure. So this was docked without any knowledge of the crystal structure at all. We probably could have run some ring sampling or increased the effort and it would have been perfect, but you can see that with this quick example that the superposition is pretty decent. so we can also compare it with the one RT4, and they overlay pretty well. Okay. So that's an example of the chemical superposition. If you were in a situation whereby you had a number of known binders, but you had no idea of the, here we use a template. So if you're in a situation where you don't have a template, you can use chemistry, APF tools, superposition, and then choose multiple APF alignment. And that will run a simulation whereby it tries to fit the chemicals and superimpose them in the most energetically favorable pose, and so you'd get a stack of conformations for a table. So you can read in an SDF table and then superimpose them on each other, and you can align them that way. But in this example, we had a template from the crystal structures. So we assume that's pretty decent pose to start with, and so we docked onto that pose. Okay. So the next step might be we might want to do some virtual screening to this these lead inhibitors. Somebody said there's a problem with the sound. I don't know if anybody else has any issues. Maybe it's just cutting in and out. Sorry about that. So we have this we have these two ligands. This is a model because we read it from this table. So we need to convert this to an ICM object. So what we're going to do now is take these 3D these ligands, and then we can screen a database of chemicals to them and score them and see how well they fit in to the APF fields. So we need to make this into an ICM object, so we can right click on it and choose Convert PDB Chemical, and we'll keep the geometry because the geometry is fine, and just go OK. So we have these two ligands. So I have a database from Chembl which contains a number of other HIV reverse transcriptase inhibitors. So I just read that in, and we can see it here. We have the activity from Chembl and other chemical names in the table. So it's a database of 150 other chemicals. So we can screen these chemicals and see how they fit into the 3D pharmacophoric fields. Thank you very much for getting back to me about the sound. Yeah, a few people have issues. Some people don't. So that's good. I don't know what's going on, but anyway. So we have this template that we're going to use, and we're going to screen this table to this template. So how do we do that? We basically we go to chemistry. Now we're using the APF tools, and we have the option called Screen SD File or Database versus Template. So we click on that. It asks us, we're not actually docking from this table. This file is saved locally on my machine, so I just need to go to Browse and find it in here. And then it asks for the template. So the template could be one or more ligands. I'm going to use two. I'm going to use the ones we just using for the example. Once again, we have the effort. You can increase that if you want to. Sample rings, sample cis-trans, sample tautomers, score, envelope fit. But because we're screening, it's going to automatically score it by APF score, but you can also add another option here. You can evaluate the strain of the ligand as well. This is a cutoff, so if you have many millions of compounds, you don't want to dock all of them, or you don't want to report the score or the 3D object of all of them. So this cutoff is quite useful to lower the hit, to make the hit list a bit more reasonable to work with. You may want to do a small test, as I mentioned before, to get an idea of the range of the score. you can redock the ligand to itself and you'd get a APF score. You could use that as the threshold and maybe lower, increase it a little bit so you can see some hits. And there's also the advanced stuff as well, so you can weight it by different weights or even atom occupancy. You can change the occupancy of these atoms and weight it by that. But this, you can just go OK, and then it will start the screening. And 150 chemicals should be like maybe a couple of minutes, but I already have run it, so once it's run, it's going to show you. Okay, file, I've got the answers here. So similar to the hit list, similar to the virtual screening, you get a hit list. We got a column called score, and so you can sort the column using the toggle here, and we could maybe add some more properties to this table, molecular weight, log P, solubility, and then we could plot molecular weight against the score, or let's do log P against the score, and a couple of outliers here in log P, and then we can change the coloring. This could help us size based on. So this plot could, if we imagine that we had millions of compounds, or a hit list of maybe 10,000, we could use certain properties here to filter the template out, and you can use this to, maybe we could select all the ones with log P below 5 or whatever here. So we have the hit list. You can view the ligands docked by clicking on this button here. I've got the fields displayed. So these fields are just generated in the same way as before, going chemistry, APF, consensus, pharmacophore here. And so yeah, you can toggle these on and off. This one, for example, the bulk of it fits well, but it sticks out of the fields that we use for screening. So it was possible that I didn't calculate it, but if you had the envelope score, this one would have got a very poor score in terms of fit, but the rest of the molecule fits very nicely. This one does as well. So you can toggle them through. So the lower the score, the better the fit into the APF fields. And if you check the box and envelope score, you'd get another score here as well. Okay, right. So that's virtual screening using APF. And so the next example is 3D QSAR. So I'm just going to delete all. So the example, so all these examples are actually online if you want to play with them yourself. This one's QSAR APF. Okay, so this is the situation we're in. I have a number of lead chemicals shown here. So they superimpose. They've all been superimposed very nicely using the alignment method that I showed earlier. So these are all. This example is based on the thyroid hormone receptor inhibitors, and the example uses experimental PKD values from Kemble for the training set. And so we have two sets here. We have a training set and we have a test set. So we're going to train our model using this training set. So in order to use the 3D APF fields, we need to first flexibly superimpose our training set onto our template. So we would go to, let me just double check. So first we need to superimpose these molecules into our 3D. We could display the APF fields just to make it obvious what we're doing. So go consensus. So these are the atomic property fields shown in the clouds here. So we're in a situation whereby we have some lead compounds. We have over, let's see how many, have 151 molecules with KD values. And so we're going to try and train this model to understand how well these fit into 3D to APF fields and relate that to the PKD. So first we need to dock all these molecules into these fields. So we go to chemistry, and we would use we go to the superposition option again, and choose flexible APF superposition to template, as we did before. So this is our template. It consists of over 1, 2, 3, 4, 5, 6, 7, about 8 different molecules. So we're going to dock these chemicals into here first. So you just go OK, and that will generate a. I've got all these. That takes a little bit of time, obviously. So I have it already prepared. So the training set superimposed. So then we'd have the table, our training set table. We get a new table called superimpose, super, and it's telling us that it's superimposed on this template here. So now we have all our training set molecules. You can see, you can toggle through. They're all superimposed into our template fields, like this. So now we're going to try and build a model. So inbuilt into ICM, there's a number of different machine learning options. And so to start building this model, we go to chemistry, go to APF tools, and then choose APF 3D QSAR. And the first step is to build the model. So we need to start learning. So ICM needs to learn how these molecules fit into the fields and what contributions give rise to the PKD value. So we provide the chemical table for training. So that would be this one because it's the one superimposed. This is the training set superimposed. And the column is PKD, which the activity column. This could be any other column with whatever you're trying to train, basically. And so we go OK, and that generates the model. So the model takes a little bit of time to run, but when it's finished, I'm just going to go here, go here. When it's finished, you'll get the model shown here in the ICM workspace. And so this is the model we can use to predict KD for other chemicals, basically. So if you want to look more detail at this, you can click here, and get some values about how good the model is, such as RMSE and some other values for R squared values. So the R squared is 0.8. We can look at that in a different way. So when it builds the model, it also produces this table called basis, and you can see the quality of the model by predict by just plotting the experimental value against the QSAR prediction. So we can just go here and then plot. That's the other, and then we can. So we have a plot here of our PKD against the predicted the QSAR model KD, and so we can add a line, a least squares fitting line here, and we can see that it might be hard to see in the go-to meeting, but the R2 value is 0.82, so it's a decent model for this. Okay, so how do we use we have also inbuilt in this example this test set. I have the KDs just for comparison so we can see. But in a normal situation you just have the ligands that you want to see the predicted KD value for these based on this field. So in a similar way we need to, these are the molecules we're going to use to predict using the 3D QSAR model. So we go to, we need to superimpose again our testing set into the 3D fields. Getting this. So we would go to the chemistry again, go superimpose, go to flexible APS superposition template, and then dock this test set into our 3D pharmacophoric fields, and have the answers here. So go file, open, and okay. So then, if these are superimposed, we then run. So this is our test set, and then we can run the prediction. So we go to chemistry and then go to APF tools, APF 3D QSAR, and then predict. So it's asking us actually got the results here already, but you need the table with the test set with the superimposed ligands. So in here, so this is that table. It's going to use the mole column for prediction, and it gives you some coloring for how well the contribution of each atom is to the score, to the prediction of the KD. So just go OK, and it runs that prediction, and you get this table with the APF QSAR PKD versus, and in this column here. So we can plot the value here against the experimental one, and hopefully we should see some correlation, a reasonable. You can add the line again here, these square thing, and go OK. So we can then read in other molecules. We could read in another set of inhibitors. We would need to then go to chemistry, superposition, and superimpose it to our 3D APF field template, and then we would go to APF tools, 3D QSAR, and predict again, and you get another prediction. There's other tabs here where you can color, or you can visualize the fields and the atom contributions to your model from the template. So it's APF, that's the 3D QSAR. So we're going to leave the webinar at this point. All these examples are online if you want to try it yourself. This is quite complex with all the different tables, but you can see that the tables, when they're superimposed, they have this super underscore value, and you can use